So hello everyone. I wanted to talk to you guys about event-driven automation. This isn't going to be your typical talk on automation. I'm not going to go into the weeds on languages or tools. My talk is going to focus on where we are today with automation and what is possible. I'll look at how we've all been doing some form of automation all along. Before starting though, I'd like to give props out to Edward Arcuri. He was going to be my co-presenter. He provided a lot of the content and the idea for EDA, but he couldn't be here today. So in Eddie's place, I'd like to introduce my co-presenter for CHI-NOG 07. J. Kitty. So what does automation mean? I'm sure many of you have managers and CXOs all wanting some form of automation. Raise your hands. When you think automation, do any of these words come to mind? Many people associate these words and others with automation, but you see, we get caught up with the specific tools and languages that are constantly evolving. At the core of automation is a process. It's a constant process to improve workflows across IT. Even within technology, we need to break this problem down into smaller phases. The first phase is day zero automation. This is where you should look at getting started. Many already have been doing it for years. It lays the foundation for the sophisticated automation that you'll want to build for your organization. Day zero automation lets you ease into the automation transformation journey. It targets the low-hanging fruits, such as communicating with devices, using scripts to automate device provisioning, automating daily operational tasks. Now, there is a famous story about how Jeff Bezos wrote an internal memo mandating, back in 2002, all engineering teams to use only service APIs to communicate with customers and across teams. This change was fundamental in transforming Amazon from just a bookseller to the world's largest cloud infrastructure provider. Therefore, the importance of this step can't be overstated. Day zero, this phase is also referred to as the human-driven automation, because the human instructs the machine to perform certain tasks in a programmatic way. Also, in most cases, the communication here is one way, or open loop. The human to the machine. Day zero is what we've always been doing for the past 20 years. Yes, there are frameworks that make it somewhat easier, Ansible, Salt, Puppet, Chef, but it's still all the same thing. Humans pushing configs, retrieving some information about the device, the network, or change, and then making a decision on what to do next. The next phase is day one, or event-driven automation. Once we have provisioned a device with day zero automation and it's in service, we want to collect information from this device to understand how it's performing and how to fine-tune its performance as required. So we build a closed feedback loop between the machine and the human. The device sends data on key metrics using telemetry, and we use automation to detect events based on these metrics and take actions on these events. While this may seem like a fully automated cycle where there is no role for the human actually plays an important role here to build the rule base, logic that drives the decision engine. This phase elevates the role of a human as the brain that ties the events to the business logic and builds rules that determine the actions to be taken on these events. The next phase in this evolution is day N, or machine-driven automation, where machines are not just taking actions on the defined rules, they are also defining the rules themselves. Of course, they do call in the human when they get stuck and don't know what to do. Has anyone seen Kariti Kampelas talk about SDN? And I'm not talking about software-defined networks, but self-driving networks. If not, it's on YouTube, take a look. He makes analogies about self-driving cars. Day 0, you tell the car where to go. Day N, the car gathers telemetry, traffic, or reads your calendar and knows where you want to go and adjusts accordingly. Day N, the system's smart enough. It recognizes that you've gotten in the car the same time for the past few days and gone to the same location, maybe to pick up your kid from school, and learns itself where you'll be going. So self-driving cars may not be too far off, but the level of automation is already here. Day 0, we have a GPS, right? Plots the course and time to destination. Human-driven, though. Day 1, Google Maps takes into account traffic, telemetry, knows where you want to go based upon your calendar. Day N, Google notifies you that you should leave by 7 instead of your regular 8 a.m. to catch that 10 a.m. flight, 90 minutes prior to your scheduled departure, all taking into account the extra time due to the accidents and weather delays on the I-90. By automation, we are talking about a focused, well-funded, and never-ending effort to identify core business processes, measure their current effectiveness, propose redesigned processes that are more efficient, test and implement them, and measure the resulting effectiveness. This isn't really new. I'm sure many have seen this before. If you've ever been involved with Six Sigma, this is the familiar DMAIC: define, measure, analyze, improve, control. Automation doesn't necessarily mean using Python, Ansible, or many of the other tools out there. It's about defining and refining a process. Think back to when you first troubleshot a network down problem or created a mop. You learn things, maybe generic things, maybe specific things about the network, both good and bad. The next step you took was to learn from those, and the next time you created a mop or the next time you troubleshot, you help streamline this process, make it more efficient. So all along, you guys were already doing this. Today, when people think about automation, they think about two things. Either they want SDN to solve their automation problems, or they think of automation in the context of configuration management. First, when the concept of automation initially started to gain momentum, it was wrongly interchanged with SDN. SDN is for service delivery, and it does use automation concepts to ensure that delivery. However, it does not apply those automation concepts to the network itself. There was an assumption that vendors were creating an automation pill that would fix everything via SDN. SDN this, SDN that. But there's no such thing. Second, configuration management is by far and away the dominant view and perception of network automation. But there are other things that we can do to bring disparate systems together to create a next generation of automation. Systems that abstract away the need for constant human intervention to run automation tasks on a network. The importance of automation has been talked about ad infinitum, and along with their talk has been the use of technologies that allow for automation to occur. But these technologies just give us a new way to do the same thing we've been doing for the past 20 years. When we talk about automation, most of the time it is in the context of provisioning. How do we provision a new data center? How do we test a change from engineering? How do we get it into production? Things like that. But that's really only a piece of the picture when operating a network, right? We put things into production, and then what? Someone needs to manage and operate it. Infrastructure has a life cycle. Not only do we need to provision it, but we also have to monitor it, we have to understand it, we have to be able to respond to changes in infrastructure, and we have to maintain it going forward. Two of the key areas of automation that we are focused on are how operators should drive change into the system and how to respond to events impacting that system. We've done a very good job of implementing technologies that up until this point take on that first part of that statement, namely how operators should drive change into the system. We do things like declare the intended state of the system and push it through the means of a workflow. But that doesn't really do much for the true operational aspects that come after the provisioning piece. This is where responding to events impacting the system is lacking any sort of automation. And any automation that does occur in reaction to an event is most likely initiated by a human. And the result of that automation is also analyzed by a human rather than an automated system. Automation and orchestration today is something called linear sequence. The concept is that we do what we want and fire it off. We watch those steps one after another in sequence. For example, runbooks. Runbooks are rarely able to understand what happened through other runbooks to evaluate what needs to be done within the runbook executing. And the runbooks are run in sequence, and that can take a very long time to run. See a problem? There has been a lot of work already done by smart people that are true automation engineers. We can look to what they have done to increase complexity, but be able to manage in other well-known areas of automation, such as oil and gas, manufacturing, robotics, and aviation. One of the key concepts of distributed systems is being able to share information asynchronously. Async communication is a very important part of being able to send out messages at a very large scale. In an event-driven infrastructure, we need this async communication to take in a lot of information and make decisions based on this influx of information instead of looking at it from that runbook perspective. There are many examples of automation in other fields, especially when people's lives are at stake. Anyone use electricity? The grid is a good example of automation engineering. It is treated as a single, massively distributed system. It has intelligence to shift resources or even protect itself. It has the ability to reroute power to restore service in case of equipment failure. Or how about an unexpected overload to the grid? Think triple-digit summer here in Chicago. ComEd, with your approval, will cycle off the power to your AC unit to help alleviate the overall load on the grid proactively. How about if your network could shift non-important traffic, maybe to slower links, maybe buffer it, and I'm not talking QoS, but dynamically based upon past history, and what if the network knows of upcoming demands? PCE, anyone? Since we already know that automation is not a all or nothing proposition, it implies it can vary across a continuum. The continuum is made up of stages and levels, and where a particular workflow is within the stages, and at what level is where in the continuum that particular automation exists. Several levels of automation have been proposed over time. A commonly used scale of LOA is shown here, and this is what most automation engineers use to determine at which level a certain task is automated. As network engineers familiar with any modern routing protocol will recognize, network devices already do this, and mostly at LOA of 7 or higher. The Stryker's SPF algorithm is part of a process that operates at LOA 8. And a human only knows that something or nothing automatically happened by asking, usually through an operational command. Most network operators, however, are at level 1 today. Those that have delved into automation to some extent are mostly at level 5, but only with specific use cases. With that in mind, and the implementation of network automation technologies still in its infancy, a stretch goal will be get to level 5 across the entire operational landscape and implementing some of the level 7 or 8 for specific use cases. And just to make these things a little bit more, we'll call it applicable to home. Level 1, the computer offers no assistance. Human must take all decisions and actions. PBR. Computer offers a complete set of decision action alternatives. You can say iOS, Junos, EOS. Narrows the selection down to a few. Command completion. Suggests one alternative. Defaults. Executes the suggestion if the human approves. Commit. Allows the human a restricted veto time before automatic execution. Commit confirmed for the OSs that have that. Executes automatically, then necessarily informs the human. System health checks, right? Monitoring the system. Informs the human only if asked. Show commands. Informs the human only if the computer decides to. We'll call that machine learning. And then finally, level 10, the computer decides everything, acts autonomously, ignoring the human. So in all seriousness, we need to decide what should and should not be automated. We were actually just out in the hallway talking about, we'll call it some financial issue that happened where, hey, I think this is a great idea to automate, and tens of $millions later, not so good of an idea. Maybe level 10 for data gathering and reporting of issues, but not necessarily for taking action. Incongruence with LOA are the stages of automation, or SOA. Stages are a way of describing system function equivalents to human response processing for any given situation. Human response processing is something we do every day, but we do not think about it as we are not cognizant of it. We just do it. For our purposes, we will use a simple 4-stage model of human information processing that can be translated into equivalent system functions. Information acquisition, information analysis, decision and action selection, action implementation. Each of these functions can be automated to different degrees or levels. The multiple levels shown before can be applied to any of the 4 stages, but some stages may have a differing level than other stages. For instance, in a network automation situation, levels 2 through 9 aren't needed in analysis stage because it's either analyzing the data or isn't. Therefore, it's either a level 1 where the human does the analysis, or level 10 where the computer does all the analysis. The choice of the optimal level of automation in a specific stage is about matching the automation capabilities available to a number of operational situations at each stage and performing the LOA versus the value of automation performed. So how do we make that decision? First, let's take a look at some very basic control systems theory. Some may remember this from their university days, especially if you studied engineering at all. And if you haven't ever heard of control systems, trust me, what I'm about to tell you is probably the most basic day one tenet. But it makes sense for us as network engineers and how we should look at automation workflow. There are 2 basic types of control systems that we will be interested in for network engineering: open loop and closed loop. If we look at a control system, it's just looking at the system that can be changed or maintained to achieve a desired output. We control the inputs into the system to have the desired output. We run a playbook, Ansible builds the config. Config sent via netconf to device or devices, then we commit. But there's no validation. By contrast, a closed loop system starts with a familiar input signal into a controller. This controller in turn sends a signal into the system, and the system generates an output signal. By controlling actions are dependent on the output, and this output is put through a feedback system. This feedback generates additional or sometimes different output based on the output of the system and feeds that into an error detector or some sort of comparator. This then generates another input signal to the controller, and then the process starts again. Now you may be asking, well, what if there is no error, or the comparison is what you expected? Following the theory, no error is still a valid input, but is nothing, thus closing the loop. As I said earlier, this is very basic control systems theory. There's a lot of information out there if you want to get more answers on this. But for now, the important thing to grasp is that we need to look past these open loop systems and figure out ways to create closed loop automation. When we think about automating a network, not just automating what humans do. One thing that we need to notice is that networks can be viewed as having processes in a distributed system. We need to try and shift our thinking of what a network is today, from unique isolated nodes sharing information to a distributed system where nodes can work independently if needed, but if they work together, much more can be accomplished. That's why you hear buzz around segment routing, PCE, a holistic view about moving packets across the network. If we look at the history of distributed systems and see the parallels of what we are trying to accomplish now, it is important to look at the three areas of distributed computing and divide network automation into what's there. This is typically some sort of service discovery or having a referenceable source of truth for all members of the distributed system. This system is capable of point-in-time reproducing the exact configuration of any element at any given time. This is usually known as configuration management today, but can encompass other items as well. Somehow using some things like a scheduler or a broker to allow for these elements to work together to accomplish a task, to coordinate these tasks. However, this scheduler or broker may block the source of truth based upon criteria, policies or rules that define how and when the elements may perform any given task. An example of this would be that an event has occurred on a network device that could be fixed with a configuration change. However, the scheduler blocks any element from changing the configuration based on the fact that the change is outside of a change window. And third is what we want to focus on, and that piece is known as a message bus. So far, we've discussed topics that lean more towards the academic, but may not seem like they have a direct correlation on what we need to do as far as automating networks. Understanding the previous topics at a high level will help us as we delve further into the event-driven automation. Here's an old example of EDA. So Junos has this thing called RPM, Real-Time Performance Monitoring. Cisco calls it IPSLA. You set it up to watch two links, a primary and a secondary, and measure the latency and delay. If the primary exceeds the preset tolerances, run a script on box to switch the cost of the link to the preferred secondary. This example has been in the old Junos Day 1 guide. As you can see, there is a constant feedback loop. Measure the delay and latency. If no good, then switch over to the secondary. But this is still a day one type of automation and single-sided event. EDA just means that we're receiving events from multiple places, taking those events and making decisions based upon them. It also means that we may have many parallel management operations happening at the same time in a seamless, cooperative way. Think about it this way. Network down. Everyone's in the war room trying to figure out what's happening. Each engineer has his or her specialty, all funneling up their finds to a manager or lead engineer making the decision or call. There's nothing new here. Back to the war room example. Events, data gathering and finding from various engineers, getting rid of the red herring, using some kind of message bus, chat, IRC, Slack. Once there is a consensus, take action. Mimicking what we do naturally as humans, just automated. Events, streaming telemetry data, watchdogs, filters with some logic, message bus, maybe salt, runbooks. Of course, there is always the other side, some disadvantages. People want things now. How about double failures? Has this network ever seen this event? Or is this just a change in end user behavior? DDoS? Or is it the new iOS upgrade that just came out? This is where things like machine learning will come into play. I read an interesting comment regarding Uber. We all know Uber is set on a path for autonomous driving vehicles using AI and machine learning. Now think of it this way. Think of those Uber drivers. They're not really drivers, but they're teachers teaching the Uber AI how to effectively drive autonomously. We may be soon teaching the network AI on how your specific network should be running. EDA is designed to be distributed with everything interacting through a bus rather than directly with each other. This allows us to scale mainly because things like queuing and blocking don't have to happen, with each listener be able to simultaneously perform its task because it received information, not instruction. This also means that things can be loosely coupled and there is no intent dependencies between any two parts of the system. We can force these dependencies to allow workflows to happen in a certain order, but it's something that we would have to make it do, which is a bonus since now we aren't tied to any interdependencies. We can now have an automation backplane that can interact at scale within the network. Think back how we as humans interact on IRC or Slack. It's the async message bus, but with systems looking 24/7 at each piece of information and taking action if the data is important to itself. This offers complete lifecycle management, and not just pushing configuration, we can now monitor, measure, and react without actually having to ask for anything. Everything can be interacted with in a common way, and because it's programmable, we are able to use existing systems, not have to write new whole applications to do things we already did. For example, there's no reason why you can't use all your Ansible playbooks, PyEasy scripts, using that concept of event-driven automation. And that's the point. Take what we already have worked on and make it better. In summary, to be able to build scalable systems, we need to adopt the lessons of distributed computing. To get more benefit from automation in networking, we need to be able to migrate from simple, old, open loop systems that only initiated workflows to thinking about how we create reactive programmable systems using closed loop automation principles. And to be able to do both of these things, adopt lessons of distributed systems and to migrate to reactive systems, it all starts with an event bus in understanding the concepts of publishers for subscribers, starting to think about workflows, how they are constructed, and how they can be chained together to fully automate the operational lifecycle of a network. Now, this might sound fairly daunting and hard, but as you will hopefully see, as we take these theories and put them into practice using technologies that are available today, that the implementation of this is relatively simple, and once you understand the concepts, implementing the technology is easy. Any questions? Comments?
So there are people doing this research. There, the folks who develop Siri and those kind of researchers are actually looking at doing this. I think the challenge is, one, it may put some vendors out of business for some tools, but second is getting people to adopt this and trust that this will work in practice. So how would you see kind of overcoming those things?
Well, to your point, right, there's a large number of, we'll call it large providers that are already doing this today, right? And we don't have to go through all of those levels, but I would think that if we just take some of those basic principles of automation and just adapt or adopt some of the, we'll call it feedback mechanisms. As I mentioned, you know, again, we were out in the hall, we were talking about we'll call it a Facebook incident, right? That there was an automated provisioning that just widely spread throughout the entire chain. And if we just had a feedback mechanism that said, hey, that's not cool, we could have prevented it. So I think it's going to be a slow step to trust these systems, but I think if we do some level of there, I think we're going to be able to essentially not step on our toes. Some of the other far-off stuff, I would be kind of leery, but you know, I think it's eventual. All right, one other thing I wanted to mention, I have some special gifts for everyone here. Just all I ask is you either tweet, include JKitty, and I'll tell you the story and give you a gift. Thank you.